Okay. So now let's move on to okay. So this is kind of big picture. So we want to find the optimal decision, right? And then in the multiple decision setup. And then the bottom line is we should use this backward induction. So that's the first thing. And secondly, when you compute this conditional expectation, we need to use identify the distribution, right? So then we use this kind of suitable and SRA and positivity assumptions to identify the model and estimate the parameters, noise parameters, etc. And then now, so then main approaches for estimating the optimal, right? Can be classified into three categories. The first one is a regression-based approach. It's called Q-learning. Second one is a semi-parametric approach using the contrast function, A-learning. A-learning is abbreviation of advantage learning. So advantage is what you can achieve best, right? Compared to other options. So and then value search estimation. So this is three. We already review these three methods for k equal 1. Was right for a single decision rule. We already studied. That was a part of the. So that was a chapter, lecture notes, chapter 3, part 2, and this was a lecture note for chapter 4. So that was kind of a method that we reviewed already, but now we're going to apply to multiple decision cases. So yeah.
A is not for all.
No, actually, because of that. Oh, right. Yeah, advantage.
Still, it's use the same idea of augmentation.
Well, actually, that is actually so you are talking about the
the value search
value of the the AIPW, right? Right. So that actually applies to value search. Okay. Yeah. So today, so this is today's coverage. I plan to cover these two, and next Tuesday, next week, I'll briefly summarize the method for the value search. So basically, these two uses a sufficient condition. So the one sufficient condition is what? So this is our goal, right? Our goal. But the sufficient condition for this one is to choose, right? Argmax Q. Something like that, right? AK. A. So that was, by the way, this one is a condition expectation of the outcome. A. Something. So actually, yeah. Yeah. That's right. Something like that, right? History. So this, if you choose this one satisfies this, right? So that means this is a sufficient condition. So these two methods, Q-learning and learning, use this sufficient condition, while the value search estimation method does not use this. It directly figure out a way, so uses an estimator of the value and then compare among different these. Okay, that's kind of a big picture. So So here's a summary of the Q-learning. Basically, this is what I already explained using the TOEIC homework example, but still, so start with Y, right? Start with Y. So start, okay. So there's no Y actually. You can start with Y and start with K equal to capital K, the last step, right? And then basically at decision K, we compute conditional expectation of a value, the value function, given the current history and at the decision that we want to choose, right? And then once you compute this Q, you can find the maximizer with respect to the argument that will become a function of the history, right? So then that is a optimal decision. And then you are not, so this is not the final. You should use this one to update your value function. So basically you use this one and apply to QA, right? And then evaluate the Q function at the best option, best decision at that time, which basically carries over the carry over your best this value of the potential Y to apply to your Q function. I'm sorry. Are you talking about number 2 or number 1? Okay.
And then the output of 3 plus 1 equals to Y.
So yeah, well, so X, so there's no actually XK, right? I mean, K plus 1, X is just, so we don't really, I guess it's probably just to use this one then. Okay. So, but here, right?
In the VP plus 1, you also have XK plus 1,
Right. So that's why, that's right. I guess I just want to write it as a single rather than you could define Q capital K, HK, capital K, AK as an expectation of Y given X bar K and A bar K, right? So, and then for capital K and for small k, you can just use it. So that's another way. Basically, we just use the outcome to compute the Q function, but the outcome should be carried backward with the best decision at the time. So so that means for K equal 2 at decision 2, we just use the project the model for the Y given X and A, right? I mean history and A. And then now this is just a kind of regression model. And then beta is the regression parameter. Beta 2 is a regression parameter, for example. Then you this is kind of estimating equation, the usual estimating equation. This could be a variance covariance matrix, right, of the regression. But usually this is you have a Y minus the mean function and variance, and then partial derivative of the mean function, which is kind of usual a GE type equation, right? Estimated equation. And then this one, basically, because you observe this random variable, right? A and H and Y, you observe this so that you can estimate the parameter. And so once you estimate the parameter, you plug in, right? And then maximize over A2, maximize over A2 to obtain the optimal decision at K equal 2. And then apply it to your Q2 function. Apply to your Q2 function and plug in. So that means you conditionally, right? Given the history, you are going to apply the best decision at K equal 2, right? And then in this case, this the meaning of this Q2, which is the value we had 2, will be the expected outcome, right? Expected outcome under the best decision at K equal 2. So that is the role, plays the role of the potential outcome on the best decision at K equal 2. So it is sometimes called the pseudo outcome. Pseudo outcome for the next step. Because here we observe Y outcome already, right? Here we observe outcome. So it's no problem for K equal 2. But for K equal 1, we don't observe Y. So we use this value function as if it is an outcome and apply regression. Okay. So that means we are kind of, so the meaning of the regression is not the same as the usual regression. The meaning of this regression, I mean, the condition expectation is that the expected Y at the best decision at K equal 2, right? So this one already utilize that we make the best decision at K equal 2, and then try to compute the conditional expectation in terms of the X, right? The available history at K equal 1 and A. So that that is the same kind of estimated equation, but the Y variable is now changed, replaced by the value function. Okay, and then use that to obtain. So you now have a Q1. So Q1 we take the maximum to obtain the optimization at T equal 1, right? K equal 1. And then this one is the value function in terms of X1. So that basically means that we have a 1, right? And 2. So the first one is the optimization at K equal 2. And then this one is the optimization at K equal 1. And then the final optimal regime is that we use this one at T equal 1, K equal 1, and then for K equal 2, we basically use the best decision at K equal 1, because this one is a history, right? This one is actually a history, but this history is a X1, X2, A2, A1, right? So this history is actually, you should apply this optimal decision at K equal 1. Okay. So that means I use the best decision at K equal 1, and then on this best decision, I will have a history, and then under that history, I have a best decision at K equal 2. I'm sorry? So now forward, right? So actually, that's right. When we make the decision, so choosing the decision, right? Choosing, obtaining this optimal decision is a backward. But this is a conditional on the history. So this is for any choice. So this we need to. So that means we need to So H2 is actually H1 and A1. I mean, sorry. X1, X2, and A1, right? So that means this guy should be fixed. So that means even though we choose backward, but then once we choose everything, then now the final answer should be forward, because it should be tells of history, and the history was determined by your choice in the previous step.
So I do not understand why we need to use X2 star. Then.
Huh?
I do not understand why we need to use X2 star.
Ah,
I think it's just X2. Because this is the outcome of X2 given the optimal decision evaluated at X1. Right?
so
This is not should be potential.
In that case, I think the one who's ideal, Q1 should also be replaced by A1. So certainly,
The observed A1 is the D1X1.
right, yeah,
Because given X1, we use D1 as our A1.
yeah.
Yeah, so then the X2 evaluates as D1 should be the observed X2.
so well, I think this one is random.
Right.
So even though you fix it, right? So X1 is given, right? X1 is given, and given X1, you have a rule, so you determine
Right.
A2. But even though you determine A1, right? The best A1, you still have a random variable.
Right, but that random is not potential. Potential means that so it's just that if I give like A1 a different value, then it's potential X2. So no matter whether you write X2 star or X2, it's all random.
Well, if you okay, so this is the realized value, right? Even end of the day, this will take a particular value.
But yeah, I just say we probably should not put star on X2.
But under D1 optimal, that's what it should be potential, right? Under this D1 optimal choosing it as fastest stage. Then under this.
I guess
It's
actually it doesn't really matter, right? I mean, you don't really. So I think given this one, right? Given this one and this one, you can write it as a X2. X2 and the T1 optimal, right? T1Q. I guess this is right. So yeah, I think I see your concern. So we can I think we can equivalently write it as a Q2 OPT and X1 X2 T Q1 OPT X1. I see. Right. Yeah. Probably this is probably better. Yeah.
Some of the notation they use that version also that you know.
Huh?
So they also use that version in some of the theorems that you know.
Version?
They use both of these versions in terms of X1, X2 or X1, X2 X3.
I see. Yeah. But I think right. I agree with you. I think this is probably better because the decision is based on what you observe, right? So right. Yeah. Thank you. Okay. And then this is just the estimate of the value under the optimal. So I think one criticism would be that maybe we need this kind of model, right? This model. So maybe the model here, here the parametric model for y on everything else is maybe okay, but how you really this is involves a maximum, right? So how you actually compute the parametric form of the model, that's not easy. So so basically parametric model assumptions from model miscalculation errors, and the model error can accumulate because you keep sequentially modeling, so that may be serious. So I think in the reinforcement learning, or in that area, they use deep learning to construct a Q function, so that they can have a better avoid this miscalculation problem. But then the interpretation is a little bit difficult, and it's difficult to incorporate the subject domain knowledge, right? I mean, so. But anyway, it's popular in practice. And here's a alternative approach that's briefly covered in the textbook. So, okay, so the k equal 2 is the same story, right? So the main concern is this Q1 model for Q1 is a little bit difficult to specify. So the idea is that okay, for the k equal 2 part, no problem. We just use the same idea. But then for k equal 1, here's the idea is your conditional. So here's the model. So even the A, you want to compute the conditional expectation of y star, even x1. And then this guy is a conditional expectation of the conditional expectation, right? And then this guy is equal to this guy, by definition. So you basically you can write it as a conditional expectation of U2. So then basically the only thing is that you want to be consistent. So A2. So we want to. So if you want to use this one, then you can just use this one as a pseudo outcome. But then this A should be, so A is actually A1 and A2. But we only interested in under this optimal decision. So we can use this delta indicator, which means that among the unit whose A2I is equal to the optimal decision, and then estimate the parameter for beta 1. That will give you way. So this is a slightly different idea. This alternative approach is based on the potential outcome model, while the original Q-learning is based on the model for the value function. So
James, kind of.
okay.
So the first approach is to model the value function,
Right.
and actually the backward selection value function. So basically,
Right. That's right.
Model.
Right.
So this is not like so the second approach is more like a statistic modeling approach, right?
Right.
Because the first approach it's hard to say whether the model is satisfied.
Right, that's right.
Because it's, everything is random, right?
Right,
So
right,
when
right,
you maximize, it's random and
Right, right.
kind of model a random
That's right.
function.
Right,
So the second approach, I think it's more public, so easier
right,
to study
that's right.
statistical property.
right.
Yeah, but I do not understand when you estimate the beta one, why you just focus on delta?
I see. So because, yeah, that's a good question. So basically this potential outcome here is for the whole A. It's not just, so you have A1 and A2, right? So then here, for example, this one is a potential outcome of A1 and A2 given X1. Then the randomness. So basically we want to fix. So this is for particular A1 and A2. So for particular and A1, A2, this is a kind of model, but in the data, so in the data, we want to recognize, so we are only interested in backward decision, right? I mean, we are only interested in the model. So this conditional expectation, we are okay. I guess we are only interested in the conditional expectation, modeling this conditional expectation under this choice.
And I'm thinking we have a model,
Right.
for mu1 and mu2,
Right,
which is independent of the backward selection procedure,
right.
right? So it's just a model
That's right.
for the data, and we have the just a model
Right.
for the conditional expectation of
Right.
the y star. So then we can use our data to estimate the beta one, beta two.
Right.
So still, this is independent of the backward selection procedure.
Mhm.
And once we have beta one hat and beta two hat, then we perform the
Right.
backward selection.
Mhm.
So then I'm just, I do not understand why when we estimate the beta one, we just focus on the backward selected.
Because I guess the model here. So this is actually this beta one is A specific,
Right.
right?
Right, but that we didn't say that A has to be like the optimal A from the backward selection.
Right.
It's
So
just a general
this
A.
beta one is actually beta two and beta. So beta. Okay, let me see. At least so this beta one is A specific, and what we really end of the day, what we care about is this particular A2. So that's why.
Okay.
Okay. So because this is actually conditional model, right? So you are conditioning on this one, then this for different choice, you are actually feeding different you will have a different coefficient. So this is actually A1, right? I mean,
So you basically say that for different A, they have a different mode of beta one.
right.
Okay, and then what about X? So the beta one should be the same for all the X1.
Right. Yeah, but X1? I mean, you mean beta one or
Okay.
Different determinant for a choice of ion. For a choice of ion, right? There are like two categories, so we get two different beta here.
I'm sorry?
So we get two different beta here. If we have like A have two different values, 0 and 1. So you're saying that we estimate two different models for zero and one?
Yeah, so this is actually, this will be A1's, basically it's just if you know the parameter, so given A1, this you will have a different A1 that I1 had, but still this is a function, right? So function, then you can actually compare two functions, and then for each value you just choose one of the two. So the fact that the beta had one depends on A1 doesn't make anything different. Yeah.
When say that the capital K equal to 3,
Okay.
the first step remain the same. We can use the
Right.
beta step to estimate beta 3.
Mhm.
And when K equals to, when we are going to the second time point,
Right.
we need to match both A1 and A2.
Something like that. Right.
And then at the first time point, we only need to match A1.
Mhm.
So we for the last step, we can always use the whole data set.
So it's
When we go
actually
back on-
right, because see, even though I write this way, because beta 1 actually depends on A1 specific. So this data is actually for that, right? For the whole A1 and A2. So basically we are kind of the same problem. We are actually using the smaller data set. So basically this is a consistent. So the observed data, observed A is consistent with your optimal A, right? Something like that. So that's the limitation. That's basically the limit. So good news and bad news. Good news is that it's modeling is relatively easy because you don't have to worry about the maximum model. But this is the bad news is that this so easier in terms of the model specification, but the efficiency is not really good because you use a smaller data set, right? So that is the kind of summary of the Q-learning. But
Actually, the second approach, if you just focus on the part that match with your backward selection, is it equivalent to the first approach? Because the first approach also just look at the maximum.
but the modeling, so right, yeah, modeling could be different. And so basically, if the models are correct, two models are, I mean, then the same story, right? So concept is the same, but the actual modeling could be different. And now we're gonna move on to A-learning. A-learning is statistically more interesting because it's a kind of a semi-parametric approach. So remember what was A-learning? We use the contrast function. So A equals 0 as the baseline control group, and then just to make the comparison. So this, the difference, right? The difference from the difference in the Q function from the baseline control group is the contrast function, and instead of maximizing Q function, we propose to find the maximizer with a contrast function. Although the same, right? Conceptually is equivalent, but there's a good reason for doing that, because we don't really have to estimate the baseline control group as a parametric model. We can make it fully non-parametric. So that is basically advantage. So first of all, here's some concept. So we have a K equal 2. So that means we have a 2 control function, right? Contrast function. So the contrast function for K equal 2 is basically the difference in terms of the potential outcome. Potential outcomes with this. So this is the basically at k equal 2, right? K equal 2. So then the decision we want to compare is this one. So the second decision, A2 decision, right? A2 is J versus A2 equals 0. So that is the difference in the expected outcome if an individual who's with realized history H2 were to receive frequent option J versus control at decision 2. And then ultimate regime at decision 2 is obtained by the maximizer of this contrast function at k equal 2. And then Q1 now. What is Q1 by the way? We are using the same Q1. Q1 is the conditional expectation of the value, right? Value function, which is basically the using the optimal decision at k equal 2. So which is basically this one. And so then C1 is a difference between the Q1s, right? So that is basically this one. So you have a difference of two potential outcomes in terms of the A1 equal to J versus A1 equal to 0. And then at k equal 2, we do optimal decision. So the difference in the expected outcome, individual with realized history H1 would have before to receive a treatment option J versus control at decision 1, and then follow optimal regime at the final decision point. Okay, so that is the concept. And then now the actual modeling, here's the basically the idea. So because so now we can use contrast function to, so we can express the Q function as a baseline plus contrast function, right? And then the value function is what? Value function is the maximizer, right? Maximum applied to the maximum. So that we still have the same baseline, but then we choose the one, so maximum of them, right? So that this is the value function. Okay. Now regarding the model for Q, now see you have a semi-parametric model, right? So this is the new K is the non-parametric part, and then contrast function is a parametric part, right? And then contrast function has this. So new K plays a role with infinity dimensional logistic parameter, and beta Kj is a parametric finite dimensional parameter. Okay, and then in addition, we impose the propensity score models for AK equal to small ak. So this is the typical propensity model, right? So you have given the history, this is the propensity. So you now you can write it. So you have two index. One is the history and A. And so your sum over all possible A, you will add up to the probability will be equal to 1. So estimate and with the parameter gamma k. And the parameter can be estimated using the maximum likely estimation. And here you observe a everything, so you should be able to estimate it from the data. Okay, so that, and now we can so now using these two models, one is the semi-parametric, right? So we have two models. One is the semi-parametric outcome model, and the parametric propensity model, right? So we combine the two, we obtain this actually this one. So, by the way, k equal 1, we already right? We already studied using this estimating equation. So that is basically we have this is a mean 0, right? So expectation 0, and this one is also expectation 0. But we by multiplying, so we make it orthogonalized. So that we can either one of the model is true, then it's consistent, right? So that is essentially the application of the Neumann orthogonalization. So we're going to apply the same idea, but we now have a multiple. So the idea is we can start with the decision K, the last stage, and then move backward. So last decision, we can basically, you can see that same thing, right? We now have a subscript K, right? Because we have a K stages. So subscript K, and then this one has a subscript K, covariate, and then, okay, just the print, I guess this one should be also Ki. But other than that, it's same thing, right? But for binary, for 0, 1 case, you can write this way. For multiple, this equation 3 can be written as a, so now you have a multiple, one over the m. So 0, 1 through mk minus 1, so you have mk of them. So that means you can use, so instead of this one, you use indicator function, right? Indicator function and minus the probability of this event, right? Probability of this event is this one. So that this expectation will be 0. And then also AK here, right? AK can become a indicator. This guy will change it to this way. And then everything else is still the same. So that is basically a system of, equations, estimating equations for this parameter. But the I guess if you look at this model more carefully, basically this is a kind of conditional model, right? A conditional contrast model. So when covariate is HK and J, A equals J. So that means this method. So we have a separate, basically we have a separate parameterization for each J. So that means equation can be just, you can basically remove this summation and make a MK different equations. So that's this. Because the parameters are not really connected, right? So they are different parameters. So that means we just write separate equation. So that means what? Basically, this equation is an equation for solving beta k, J, right? Parameter. So this is the parametric part of the concept. So this is a non-parametric, right? This could be either parametric, non-parametric, doesn't really matter. But this is a typical Neumann orthogonalization formula. So you can argue that we can obtain doubly robust estimator, right? Doubly robust in the sense that either this model or this model is correct. This model should be correct, right? This model, contrast function model should be correct, but the baseline model or the propensity model is correct, either one of the two, then the expectation will be 0, so that we can get W over this. Okay. Now we, so for at least for decision capital K, it's okay because we observe Y. But we want to do the backward, right? So we want to apply the backward induction as in the Q-learning. We need to compute the value function because this one plays the role of the pseudo outcome, right? So we want to use it to do the next step estimation. So how to compute it? So this is the kind of key formula. So Y is just the current data, right? Current outcome. And this is what? Current value of A. This is what? Best, optimal. So this is the optimal choice. This is the current choice. This is the current outcome, right? So then the current outcome minus the contrast function at the current A plus the contrast function at the optimal A is becomes a value function, right? Because the value function, what is the definition of this guy? The definition of this guy is the potential outcome of this guy, HK, AK, given HK. Argue max, right? So the definition of this guy is this guy, the best you can do. So that means I should use this one instead of using this one, right? So that is this vision. Same way here, right? So that is a more generalization. But okay, so I'm gonna prove it. But let's try to recall what we did before. So to prove it, chapter, yeah. So this is basically the same proof. What is the 7, by the way? Value function. So this is the K equal 1 case, right? K equal 1. This is the current Y, right? This is what? Optimal decision. And this is the current decision, right? So basically, contrast function. So this is basically T optimal X. So T optimal X minus A, and then contrast function is exactly what we same as this one, because this one is the right contrast function at the T optimal, and this is the contrast function at the current A. Okay, so now let's try to remember. Let's try to see how we actually prove it. So forget about all this. So how we actually prove it, to prove this one to equal to this one, what we did is take the conditional expectation of all these things given X and A. Okay, X and A, and then once you do that, then this guy becomes a QXA, and then QXA is a rho X times ACX, and then we get some cancellation, essentially. So we're gonna do the same. So I'm gonna use the same idea to prove it. prove this because this is just a generalization, right? So basically proof of 6. So left hand side is a given HK AK given HK, right? So I just write left hand side to apply the conditional expectation first, and then this guy is equal to conditional expectation of the VH plus 1 HK plus 1 given HK AK plus maximum CK HK J minus I AK. Okay. And then the first term is nothing but the definition of the Q. So this, I'm talking about the red one inside the expectation. So I guess I can just write the two terms. Okay. And then Q is V nu K HK plus summation J. So we call 1 and 2. Then we can write it as a 2 minus plus 1 minus 2. So 2 cancels, right? So this is 2. This one. So that is actually equal to V. So sorry, this one looks a little bit new. This is V. Okay. So that basically take care of the equation 6. Yeah, I have a 3 page and 10 minutes, so it should be good. Should be okay. Unless you might have a question. Okay. So that means what? That means I like to use this one, right, as a pseudo outcome, and try to make a model. So basically, based on 6, which I just showed, we can compute the pseudo outcome, which is the estimated value function. Something like this. So pseudo outcome. So interesting, because at least we can backward, right? Backwardly find out past decision. So that means I can actually construct, given the current history, at the current K, I can at least use what would be my value function, right? Because this is kind of a observed y, right? This is kind of my observed y. So I know that this is obtained from this one. But what I should have used is this one, right? So we kind of subtract and then add. So that this is the value function. And then I like to use this value function to apply to my the equation, G equation, G estimation equation.
So now I have a question.
Okay.
So comparing this approach with the previous two approaches, it looks like this approach uses the kind of idea of imputation,
Okay.
right? So the previous two approaches only use the data that match to the optimal decision from the backward selection.
Right.
So this approach kind of, so even if I do not match to the optimal,
I see.
they kind of impute
The best decision, right? Best
Yeah.
outcome, right?
Yeah, to
Yeah.
impute the best outcome and to put it back.
Right.
And then, okay, so it's more
Right.
like a imputed.
I see. So imputing the counterfactual outcome, right?
Right.
Of the best decision.
Right.
Right. Thank you. That's right. Okay. So that is basically equation of the parameters in the contrast function, and then use that. So once I have the contrast function, then I can obtain this optimal decision, right? And then this is my A learning. So subscript A is used to reflect the A learning. So A learning estimator of the optimal decision. So this function is a sometimes called advantage function, right? I mean, so advantage is what I could I can do better, right? I could do better, something like that. Which in my it could be advantage or could be called regret. Because I know I now realize that I could do better, right? So that is a kind of regret. So that is actually approach that Susan Murphy used this regret function model. So she actually make a model for this something like a D minus the current A, and then something like square and times C, CK, something like that. I mean, some parametric model of the regret function, and then have a way to estimate the parameters. So just as the validity of Q learning is predicated on correct specification of the Q function, here the validity of A learning depends on correct specification of the contrast function and others. So for cap Y equal, I guess, as we carried backward, there may be some, we actually, because we are assuming that this conditional expectation follows the this model, right? So this is actually Q function, right? Q function. So Q function is actually a model of the QK of the K plus 1 given H Ki AK equal to J, something like that, right? So it so I guess but by allowing the baseline as a non-parametric, we have some flexibility, but still, the theory assumes that we need the this modeling part. So we allow this flexible, but we assume that this is correct, right? Okay. I think that's the main thing. Any questions? Yeah. So I think the concept is okay, but the actual implementation may be more difficult. Yeah. But I hope that at least the concept is delivered to you guys. Okay. Okay.